It's not a bomb. It's not an asteroid. It's not a war. It's a single flash of light on the surface of the sun. One you'd never feel, never hear, and never see coming. And in the 18 hours that follow, it could switch off the machine that runs your entire life. Not a metaphor, a physical event. Recorded, measured, and expected to happen again. Here's the terrifying part. We have already watched a smaller version do exactly this. In 1989, it took 90 seconds to plunge 6 million people into darkness. And the modern internet, the thing you are using right now, was never built to survive the big one. So picture this. It's an ordinary morning. You reach for your phone, and the signal is gone. Not weak, gone. The bank app won't load. Card readers at the store go dark. Petrol pumps stop. Traffic lights die at the same second across an entire city. The power flickers once, then quits. And this time, it does not come back at lunchtime. You walk outside. Your neighbors are outside too, holding useless phones, staring up at a sky that, the night before, glowed green and red all the way down to the tropics. Nobody can call for help, because the network that carries the call no longer exists. And the experts who warned this could happen, they've been telling us for years. Most people just weren't listening. Today, you will listen, because by the end of this, you'll understand exactly how one flare on the sun could take the whole thing down, and how close we've already come. This is how one solar flare could trigger an internet apocalypse. Today, we break down everything. What a solar storm actually is, and why the sun is capable of this. What happened the last 2 times it reached down and touched our machines. Why the modern internet has a hidden weak point almost nobody talks about. How close a direct hit came in 2012. And what a full strike would really do to your world. No filler, no fear for its own sake, no guessing, just the facts. Start with the sun, because none of this makes sense until you do. The sun is a ball of superheated plasma, held together by gravity, and twisted by an enormous, tangled magnetic field. That field does not sit still. It knots. It stretches. It snaps. When it snaps, the sun releases energy in 2 ways that matter to us. The first is a solar flare, a sudden burst of radiation, a flash of light, and X-rays traveling at the speed of light. It reaches Earth in about 8 minutes. On its own, a flare mostly disturbs radio signals and the upper atmosphere. The second is the dangerous one. It's called a coronal mass ejection, or CME. According to NASA, a CME is a cloud of magnetized plasma, billions of tons of charged particles, hurled off the sun into space. It is slower than the flare. A typical CME takes 1 to 3 days to cross the 93 million miles to Earth. The mechanism from there is simple. When that magnetized cloud slams into Earth's own magnetic field, it shakes it. And when a magnetic field moves near a conductor, it pushes electric current through that conductor. This is not exotic physics. It's the same principle that runs every electric generator on the planet. Freshman physics. A changing magnetic field drives a current. Now scale that up to a planet. The moving field induces what scientists call geomagnetically induced currents, GICs, in anything long and conductive on the ground. Power lines, pipelines, railway signaling, undersea cables, currents that those systems were never designed to carry. Here's why that's a problem. Our grids run on alternating current, power that flips directions 60 times a second. A geomagnetically induced current does not flip. It's a slow, one-directional flood, and when it pours into a high-voltage transformer, built for alternating current, the transformer saturates. It overheats. It can burn out from the inside. The current comes from the sky. The damage happens on the ground. What this means is that the sun does not need to touch a single wire to break it. It only needs to move its magnetic field hard enough, and our own infrastructure does the rest. No guessing. Just the facts. And the facts get worse from here. To understand what the sun is capable of, you have to go back to a morning in 1859. On the 1st of September that year, a British astronomer named Richard Carrington was sketching sunspots through a telescope when he saw something no one had recorded before. A sudden, brilliant flash of white light erupting from the sun's surface. He had just watched a solar flare with his own eyes. What Carrington could not see was the coronal mass ejection racing behind it. That cloud crossed the entire distance to Earth in roughly 17.5 hours. Not the usual several days. It was moving that fast. When it hit, it triggered the most intense geomagnetic storm in recorded history. The mechanism was the same one we just described. But the world was different. There were no power grids. There were no satellites. There was one piece of long, conductive technology strung across the continents, the telegraph. And the telegraph went insane. According to contemporary accounts and later analysis, current surged through roughly 100,000 miles of telegraph line. Sparks jumped from the keys. Paper tape caught fire on operators' desks. In Portland, Maine, and in Boston, telegraph operators disconnected their batteries entirely and kept sending messages for about 2 hours using nothing but the current. The sky was pushing into the wires. Read that again. The storm was powering the network by itself, and the sky lit up. Auroras that normally hugged the poles were reported over Cuba, over Panama, over Queensland, over Santiago. In the Rocky Mountains, campers woke in the middle of the night to a glow so bright they got up and started cooking breakfast, convinced dawn had arrived. In the northeastern United States, people reported they could read a newspaper by the light of the aurora at night. Here is the historical comparison that should stop you cold. In 1859, the total damage was some scorched telegraph offices. That's it. Because in 1859, that telegraph line was almost the only thing electric on Earth. What this means is straightforward and chilling. The Carrington event was not a worst-case sun. It was an ordinary catastrophe striking a world with almost nothing to break. We have spent the last century and a half wiring every part of our lives into exactly the kind of long, conductive infrastructure that storm feeds on. The sun hasn't changed. We have. No guessing, just the facts. If 1859 feels too distant to fear, here is one inside living memory. March 13, 1989. A coronal mass ejection, far smaller than Carrington, but still severe, struck Earth's magnetic field. The claim is simple. A modern power grid can fall in seconds. Here is the proof. The target was Hydro-Quebec, the utility running electricity across the Canadian province of Quebec, a network rated at 21,000 megawatts. Geomagnetically induced currents flooded into its long transmission lines. The transformers began to saturate. Protective systems, seeing the chaos, started tripping offline one after another. The entire grid collapsed in 90 seconds. 6 million people lost power. In the middle of a Canadian march. For 9 hours, and in some places much longer. According to NOAA, the outage was so sudden and so strange that, at the height of the Cold War, some feared the blackout, and the intense auroras were the first signs of a nuclear attack. And the damage didn't stop at the border. The same storm reached down into the United States. At a nuclear plant in New Jersey, a large transformer was permanently damaged. Cooked from the inside by currents it was never built to carry. Now here's the scale comparison that matters. The 1989 storm registered a geomagnetic intensity, a measure called DES-T, of around -600 nanotesla. Serious, severe, but modern estimates put the 1859 Carrington event somewhere between -800 and -1750. In other words, the storm that took down a modern grid in 90 seconds may have been less than half the strength of the one that lit up Cuba. What this means is that we are no longer speculating. The grid-killing mechanism is not theoretical. It has already happened, to a real utility, in the modern era, and we watched it unfold in real time. Quebec was the wake-up call. The question the rest of this story asks is simple. What happens when the alarm is louder, and the thing at risk isn't just the lights, but the network underneath everything? No guessing, just the facts. Here's where most people get it wrong. They assume the internet is safe because it's digital, wireless, everywhere, spread out, impossible to switch off. The reality is the opposite. And it comes down to a single, physical vulnerability that a computer scientist named Sangeetha Abdou-Jyothi laid out in 2021. Abdou-Jyothi, then at the University of California, Irvine, presented a paper at the SIGCOMM 2021 conference with a blunt title, Solar Superstorms, Planning for an Internet Apocalypse. It was the first serious look at how a solar storm would hit the internet's physical backbone, and her finding was not what you'd expect. Start with what's safe. The oceans that separate the continents are crossed by long-haul submarine cables, the true skeleton of the global internet. The optical fiber inside those cables carries data as pulses of light. Light doesn't care about magnetic storms. Abdou-Jyothi found that the fiber itself, and the cables as a whole, would survive even a Carrington-scale event. So where's the weak point? The mechanism is simple. A light signal fades as it travels. So every 50 to 150 kilometers along an undersea cable, engineers install a repeater, a device that grabs the weakening signal and boosts it back to strength. And those repeaters are not optical. They are powered by an electrical conductor running the length of the cable. That conductor is exactly the kind of long, grounded, metallic path a geomagnetically induced current loves. Overload the line, and you don't fry the glass. You fry the repeaters. And a single dead repeater can take an entire transoceanic cable offline. Now add the geography, which is the part that should worry the Northern Hemisphere most. Abdou-Jyothi's analysis showed that geomagnetically induced currents concentrate at higher latitudes, roughly above 40 degrees, and longer cables carry more risk than shorter ones. Put those two facts together, and one route lights up as the single most exposed corridor on Earth: the long, high-latitude submarine cables running between North America and Europe. The comparison inside her own findings is revealing. Shorter cables, say, the dense, stubby links around Singapore and much of intra-Asia, are far more resilient simply because they're short. The Internet's backbone in the tropics fares better than the backbone in the north. And here's a number to sit with. Abdou-Jyothi cited an estimate that a single day of internet outage in the United States alone costs around $7 billion. A day. Now imagine not a day, but the time it takes to physically retrieve a cable repeater from the bottom of the ocean and replace it. Under normal conditions, repairing a single undersea fault takes days to weeks, and that's with a healthy internet and a working power grid to coordinate it. In her assessment, a global event could mean outages lasting not hours, not days, but months. What this means is uncomfortable. The internet's resilience is a story we tell ourselves. Underneath the cloud and the wireless and the redundancy sits physical hardware, in the dark, on the seafloor, quietly vulnerable to the sun. No guessing, just the facts. Now look up, because the threat isn't only under the ocean, it's also in orbit. And we have very recent proof of how fragile that is. The claim here is almost hard to believe. A solar storm too weak to make the news destroyed dozens of satellites. Here's how. On the 3rd of February, 2022, SpaceX launched 49 Starlink satellites into low orbit. At almost the same time, the sun threw off a modest coronal mass ejection. When it arrived, it produced only a minor geomagnetic storm, the lowest rung on Noah's scale, a G1. The kind of storm that happens hundreds of times per solar cycle and normally harms nothing. But the mechanism this time wasn't about induced currents in wires. It was about heat. When the storm's energy poured into the upper atmosphere, it warmed the thin layer of gas called the thermosphere, the region those brand new satellites were flying through. Warm gas expands. The air got denser exactly where it shouldn't have. SpaceX later reported that atmospheric drag during the event was up to 50% higher than on previous launches. The satellites tried to turn edge-on to cut through the thickened air. Most couldn't fight it. According to SpaceX and multiple peer-reviewed analyses, around 38 to 40 of the 49 satellites were dragged down and burned up in the atmosphere within days. It remains the largest single-event satellite loss in Starlink's history. And that was a G1, the gentlest storm on the chart. Now, scale that comparison up. The May 2024 storm, nicknamed the Gannon storm, that pushed auroras as far south as Mexico, was a G5. Extreme. The strongest to hit Earth in roughly 2 decades. The 1989 Quebec blackout was driven by a storm at that same extreme end. And Carrington, as best we can estimate, was in a class beyond even those. If a minor storm can quietly delete 40 satellites, what happens to the constellations we now depend on? GPS, weather monitoring, satellite internet, military communications, when an extreme one arrives with a direct hit. What this means is that both halves of our connected world are exposed. The cables below and the satellites above are vulnerable to the same source, through 2 entirely different mechanisms. There is no clever place to hide the infrastructure. The sun reaches all of it, no guessing, just the facts. You don't have to imagine any of this in the abstract, because we ran a live rehearsal barely a year ago. Over the weekend of May 10th and 11th, 2024, Earth was hit by the strongest solar storm in more than 20 years. Space physicists named it the Gannon storm, after the space weather scientist Jennifer Gannon. Most people remember it for one reason: the sky. Auroras, normally reserved for the Arctic, spilled south over Mexico, over Florida, over Spain and Portugal. But behind the light show, the mechanism we've been describing was quietly at work. The source was a single, monstrous sunspot region, according to NOAA, a group roughly 17 times wider than the Earth itself. Over a few days, it fired off a barrage, at least 8 coronal mass ejections aimed our way, arriving in overlapping waves. NOAA's Space Weather Prediction Center issued its first severe G5 storm warning since 2003. Then the currents arrived. On the ground, according to NASA and grid regulators, some high-voltage lines tripped and transformers overheated. Crucially, and this is the good news, there were no major blackouts. The North American Electric Reliability Corporation reported unusual transformer heating and distorted electrical waveforms, but operators had been warned in advance and switched into protective procedures, scheduling extra generation, pausing maintenance, watching the induced currents climb. In New Zealand, the national grid triggered a geomagnetic mitigation plan for the very first time and rode the storm out with no impact to supply. This is what preparation looks like when it works. But the storm found the soft spots anyway. Up in orbit, the effect was almost surreal. Researchers found that during the Gannon storm, nearly 5,000 satellites fired their thrusters and climbed to higher altitudes on their own, automated responses to the thickening atmosphere. Half of all active satellites were maneuvering in ways ground controllers could not fully predict. A mass migration in low orbit, unplanned, all at once. And on the ground, the storm reached straight into an industry most people would never connect to the sun: farming. Here's the mechanism. Modern agriculture runs on GPS. Not ordinary GPS. A centimeter-precise version called RTK that steers tractors down dead-straight rows automatically. When the Gannon storm scrambled the ionosphere, those signals went haywire. One study found GPS position errors of up to around 230 feet at the worst of it. Tractors across the American Midwest veered off course. And the timing could not have been crueler. It was peak planting season. The cost is the part that lands. Terry Griffin, an agricultural economist at Kansas State University, estimated that GPS disruption from the Gannon storm cost American farmers in the Midwest more than $500 million. From a storm that broke nothing, blacked out nothing, and is remembered mostly for pretty skies. Now hold that comparison against everything else in this story. Gannon was a G5. Extreme. The top of NOAA's scale. But the Carrington event was far beyond it. The 2012 near miss was far beyond it. Gannon sits at roughly the strongest storm we regularly survive. And it still cost $500 million. In one sector, in one region, from a single misbehaving signal. What this means is that the question, could a solar storm really disrupt modern life, already has an answer. It did. In 2024, the only reason it wasn't a catastrophe is that Gannon, for all its power, was still the small version. No guessing, just the facts. Everything so far might sound like a warning about the future. It isn't. The big one has already come. It just missed. In late July 2012, the Sun launched a coronal mass ejection that, by every measurement we have, was a true Carrington-class monster. It tore across the inner solar system at extraordinary speed, and we know it in extraordinary detail, for one reason. Of all the empty space it could have crossed, it happened to pass directly over one of NASA's stereo spacecraft, an observatory almost perfectly built to measure exactly this kind of event. Where Carrington had a telescope and a sketch pad, scientists in 2012 had a fully instrumented probe sitting right in the blast. Here's the mechanism of the near miss, and it's pure luck. The storm crossed the orbit of Earth, but Earth, in its endless loop around the Sun, had passed through that exact point in space about 9 days earlier. The gun fired. The target had already moved on. Now the data. In a 2013 analysis, Baker and colleagues estimated that if that 2012 cloud had struck Earth head-on, the resulting storm would have registered a drast of roughly -1200 nanotesla. That's comparable to Carrington itself, and about twice as severe as the storm that dropped Quebec. A full Carrington-class hit on the modern world. We dodged it by 9 days, and most people alive at the time never even heard about it. So how often does the Sun load this particular gun? Here the numbers come from real studies, and I'll mark the uncertainty, because it is uncertain. In 2012, physicist Pete Riley of Predictive Science calculated the odds of a Carrington-level storm striking Earth at roughly 12% per decade. Abdu Gyothi, applying a related range to internet infrastructure, cited a probability of a large-scale event somewhere between 1.6 and 12% per decade. Estimates of how often a Carrington-scale storm recurs cluster around once every 100 to 200 years. 12% per decade is not a small number. It's roughly the odds of rolling a specific number on a die, every 10 years, forever. And the last confirmed Carrington-scale event to actually hit us was in 1859. What this means is that the 2012 near-miss wasn't reassurance. It was a live demonstration that the shot is real, the timing is chance, and our streak of good luck has no guarantee of continuing. No guessing. Just the facts. There's a final piece, and it's the one that turns a natural event into a genuine crisis. How little warning we'd get, and how little we've prepared. When a coronal mass ejection is launched, we can see it leave the sun, but confirming its true speed, direction, and, most importantly, its magnetic orientation depends on a handful of spacecraft parked between us and the sun, and they sit relatively close to home. That means our reliable, actionable warning is often measured not in days, but in hours. Sometimes less than one. The mechanism of the problem is a mismatch. As reporting around the 2022 Starlink loss made painfully clear, the space weather forecasting system built up over the past 40 years was tuned for specific old customers, power grid operators, airlines flying polar routes, high-frequency radio users. It was not built for a world where dense satellite constellations and a globe-spanning internet are the things at stake. The warning infrastructure is aging. Some of the very satellites that give grid operators their few hours of lead time are already operating well past their planned lifetimes. And preparation is uneven. After 1989, Canada invested heavily in hardening the Hydro-Quebec grid. The United States has since introduced reliability standards for geomagnetic disturbances. Those are real steps. But protecting the most exposed transformers, at scale, across an entire continent, has moved slowly, because it's expensive, and because the disaster it prevents hasn't happened yet in the modern era. Here's the comparison that captures it. We have built a civilization that can be crippled in 90 seconds, and defended it with a warning system that might give us 60 minutes, and satellites running on borrowed time. What this means is that the danger isn't only the storm, it's the storm arriving faster than we can react, hitting systems we've only half protected, watched by instruments we should have replaced years ago. The sun sets the schedule. We're the ones who keep hitting snooze. No guessing, just the facts. So let's spell it out. Not a near miss. Not a minor storm. A direct, Carrington-class hit on the world. Exactly as it is today. Fully. It begins with a flash we can't feel. Hours later, the coronal mass ejection arrives and shakes the planet's magnetic field. Geomagnetically induced currents surge into every long conductor at once. The high-voltage transformers go first, the giant ones at the heart of the grid. They saturate and overheat, and here is the detail that turns an outage into a catastrophe. The largest grid transformers are custom-built, enormous, and there is no warehouse full of spares. Replacing one can take many months. Damage hundreds of them across a continent in a single afternoon, and you are not waiting for the lights to flicker back on. You are waiting for factories to build the replacements. Factories that also need power. While the grid falls, the sky reaches the internet. Repeaters on the long transatlantic cables burn out. Whole intercontinental links go dark. Satellites in low orbit get dragged down or knocked out. GPS degrades. Global communication, banking, logistics, emergency coordination runs on the network that just vanished. And now the two failures feed each other. You can't easily repair undersea cables without power and coordination. You can't run a modern power restoration without communications. Abdu Gyothi's estimate of outages lasting months stops sounding like a headline and starts sounding like arithmetic. The economic scale is not guesswork. According to a National Academy of Sciences assessment, a solar storm of this magnitude striking today could cost on the order of $2 trillion in the first year, around 20 times the cost of Hurricane Katrina. A separate risk model from Lloyd's of London put the exposure for the United States alone at up to $2.6 trillion. And here's the escalation almost nobody mentions. Carrington may not even be the ceiling. Evidence locked in ancient tree rings, sharp spikes of radioactive carbon-14 dated to the years 774 and 993, points to solar particle events that appear to have been dramatically stronger than 1859. We have never observed one with instruments, but the record in the wood suggests the sun is capable of hitting harder than anything in written human history. That is the worst case. A silent flash, 18 hours of travel, and a modern world knocked back toward a pre-electric age it no longer knows how to survive. For months, at a cost measured in trillions, with no guarantee it's even the biggest the sun can throw. So here's the one thing to take with you. The internet apocalypse isn't a fantasy, and it isn't a prophecy. It's a physical event with a known mechanism, a measured history, and a real probability. The sun has done a smaller version to a modern grid. It launched a full-sized version at us in 2012 and missed by 9 days. And the network your entire life runs on has a weak point most people have never heard of, sitting in the dark on the ocean floor. The good news is that this is one disaster we can see coming, if we choose to. Hardened transformers, better forecasting satellites, smarter grid design. We are not helpless. We are just, so far, unhurried. If you want to keep understanding the forces that could reshape our world overnight, subscribe. We track this as it develops. Every storm, every near miss, every step we take to get ready. And next time, we go one level deeper. The giant transformers at the heart of the grid, why we can't replace them fast, and why they may be the single most important machines you've never thought about. No guessing, just the facts. We'll see you in the next one.